Okay, thanks everyone for joining this call. I'm going to give a few opening remarks to just kind of give a little bit of context about me, kind of where I've sort of been fitting into this line of questioning, and then going to quickly then sort of dive into kind of the conceptual framework that we've been using and how we've been trying to very systematically make a bunch of decisions about how we're going to address the problems of how can we evaluate the risk of low dissolved oxygen in Puget Sound. Just quickly about me, I'm a marine ecologist. I do a lot of work on marine food webs, and since I arrived in the Puget Sound area, the issue of low dissolved oxygen has always been an issue of interest to me. I've been involved in particularly Hood Canal related work for some time, looking at how species move in response to low oxygen. And whether or not there are any changes in food web linkages that happen due to basically predator and prey having different oxygen tolerances. So it's a topic I've been thinking an awful lot about. So in the context of the thing that we were talking about today is obviously a lot of the issues are about how to manage uh, wastewater treatment in order to limit nutrients, with the goal being to protect the marine life. And it's that part that I'm at least have some capacity to speak to, is like, how do we address that question of like what are the oxygen levels that are needed to support the species that we value in Puget Sound? Big high level sort of conceptual frameworks from sort of physiology all the way through sort of risk assessment and ecology is, first of all, oxygen itself and low oxygen itself isn't itself an issue. It's an issue when the environmental oxygen levels drop below the thresholds that organisms need to do the things they need to do. So the example I always give is, while you're sitting in your room right now, there's probably plenty of oxygen right now. And if someone were to reduce oxygen by 5 or 10%, you probably wouldn't even notice it. Maybe if you really paid attention, you might notice maybe you're, inhaling a little bit more often, but you probably wouldn't notice any difference at all. But if we somehow managed to transport your office and put it like halfway up Mount Everest, and we did that same thing of like, hey, now we're going to lower oxygen 5 or 10%, well, that's a really big, significant reduction in oxygen because you're much closer to your physiological thresholds. So I'm going to be talking an awful lot about like, what are these thresholds? How do we come up with those thresholds? And then how do we relate the environmental oxygen levels to those thresholds? The second really key point is there are a lot of sort of endpoints you could consider on the spectrum of like, what does oxygen do? The one that we're most upset about is the last one listed in the second bullet, this point here, dying. That's when all the adaptive responses are no longer available to an organism. That's by far the worst outcome. But a lot of things will happen to an organism before you get to that point. The biggest one is they generally tend to move. They tend to try to find parts of the water column that might move up and down, or they might move horizontally to try to find areas that have the oxygens they need that are above these thresholds. Um, we do know that oxygens have, all organisms have a pretty good ability to acclimate to low oxygen. So they could change their blood oxygen carrying capacity, they could change their gill structures, so they have a higher surface area. There's a bunch of things organisms can do. Then, of course, over generations, you could get local adaptation, which is not a thing we're going to be considering today. So this last point, I think, is a real critical one. It's the one that we're hoping to actually provide some guidance on, is one, thresholds matter. And second, we want to ask, well, when and where are organisms present where the environmental conditions are dipping below those thresholds? So trying to look at not only the oxygen levels, but looking at the oxygen levels both in space and time relative to where these oxygen physiological thresholds are. And that's what we're try to speak to today. One last piece of context that's really relevant in the context of climate change is that both physiological theory and tons of ample empirical observations let us know that these oxygen thresholds are themselves temperature dependent. So generally, as oxygen gets warmer, marine life needs more oxygen in the water in order to maintain their functions. This is just an example organism that's quasi-representative of something you might see, where this axis here is the oxygen pressure. That's basically what is that threshold? What's that critical oxygen level that's needed to maintain life? If you're worrying about these units, a lot of physiological people who work on gas exchange like to work in pressure units, which is not my intuitive units. So these are in kilopascals, just so you know kind of where we're dealing with here. And this shows like, hey, you might get a doubling of where the threshold is from very, very chilly waters to very warm waters. And this is a very common temperature dependence that we see. Okay, so that's the context that we're sort of looking at. So one, thresholds, and then we're looking at how the oxygen levels relative to those thresholds vary in space and time. That's what we're going to try to address. So there's a lot of steps that are going to try to go into try to doing all of that. And the basic level, what we're really trying to look at is trying to look in space and time, what is the environmental oxygen partial pressure? And at the same time, for organisms that we're going to be using as our sort of our pilot cases, what are these critical oxygen levels and how do they depend on body size? And we want to identify both when and where does the oxygen partial pressure drop below the oxygen threshold. Doing this means we need to have a really structured approach to make a bunch of decisions. So on one hand, at a given location, even at a given depth, there's going to be variation in oxygen and pressure. So we need to make some choices like, well, what number do we use? There's also going to be variation with depth. So shallow water generally has higher oxygen than deeper water. And then how do we come up with these oxygen thresholds, given that not all organisms have been treated to the same robust laboratory studies? We're using the Salish Sea model. Some of you may be pretty familiar with that. Just say it's a pretty complicated biophysical model that allows us, that's been pretty rigorously tested, that allows us to map the environmental oxygen partial pressure at various depths at a variety of locations throughout Puget Sound. And I'm going to just imagine a scenario. What if you just zoomed into one place in Puget Sound on a given day at a given moment? And if you could drop, say, a CTD in the water, you would see your typical profile of, say, PO2 and temperature as you go down with depth. PO2 is on your left, temperature on the right. So that's something we would see in sort of empirical observations. But because we're dealing with a model, we don't have these lovely lines. Instead, we have a bunch of points where we have 10 different layers that represent different chunks of the water column at each location at this particular moment in time. Now, over the course of the day, we don't just have a single observation, but we have a different observation for every hour of that day. So now for every layer, we've got a bunch of different PO2 measurements and a bunch of different temperature measurements. So this is where we need to now make some choices like, well, when we're thinking about what is the PO2 and what's the temperature, what number do we use? Because there's more than one for any given day. So what we're doing in this first round is trying to make a simple and what we think is a conservative approach. So for each layer, so say right here, we've got a bunch of different PO2 measurements, and those all represent different hours of the day. We're going to assign to that layer what was the smallest PO2 we saw in the course of a day. And that's the number we'll assign to that, and we'll be calling that just the min PO2. And then we go to this layer, do the same thing. What was the smallest number? It's that. What's the smallest number? We use that. So now we're going to be looking at just what was the minimum PO2 over the course of the day for each layer, and that's the thing we're going to be looking at when we're comparing it to the oxygen thresholds. For temperature, rather than use the min temperature, we're just going to use the average temperature throughout the day. Again, that's more of just a simplifying assumption. So here we have our mean temp throughout the day. Okay, so that's how we're kind of treating all this very robust and rich model output from the Salish Sea model. Now, how do we come up with these thresholds? So I've mentioned that there are these environmental thresholds, and they're often called P-crit, or stands for critical oxygen pressure. I've been working on summarizing every study I can find where someone has taken an organism and done a particular type of laboratory study to try to figure out where are these thresholds. The data set that I've used has over 150 species, over 450 laboratory measurements, and these things span 6 different phyla, so it's pretty taxonomically broad. In a previous project, I developed a computational approach that allows us to estimate the critical oxygen threshold for any organism based on, first, its taxonomy. So what's literally the genus species, the temperature, because it's temperature dependent, also body size, because there is a small effect of body size. But then lastly, every laboratory has like a slightly different way that they did it. So I basically have a way to account for the fact that some laboratories measured the critical threshold this way, and some people measured it that way. So I'm trying to account for as many things that we can possible. So overall, then I can come up with a given species and say, like, this is my best estimate of the critical oxygen threshold. And I can even tell you something about the uncertainty in that number. So we'll be showing you a little bit of that uncertainty later on. So just quickly, what you can see, this is just a bunch of made up organisms showing what this critical oxygen partial pressure might look like. And here on the bottom, some hypothetical taxa that are well within the realm of what we see, where we see some taxa, as you know, are just super tolerant. They can have really, really low thresholds, which means they can tolerate really, really low oxygen levels without them being really, really stressed. Also, you can get some taxa that have a really, really strong temperature sensitivity. So in other words, their threshold increases rapidly with temperature, where others are much flatter. So we're able to see all that richness of taxonomic diversity, and that's kind of baked into a lot of the things that we're going to be presenting. And then lastly is when people measure this threshold, it matters like what threshold you're talking about, because it's the threshold in order to do what. So on one hand, on the left-hand side of the screen, some people measure the threshold in terms of like, what's the minimum oxygen needed just to keep this poor little fish alive? So that's a pretty low, pretty low bar. And then alternatively, some people measure it like, no, I'm not interested in that. I'm interested in, there's a bunch of things that an organism needs to do just to do minimum functions and sort of routine activity. I'm going to sort of benchmark my my oxygen threshold is what's the oxygen threshold in order to meet that higher bar. So we're going to be only today presenting the second one, but just know we have all the analysis you've seen today. We've also done for the sort of the very, very dire sort of endpoint. Okay, so taking that same graphic before, here's our model. Here's the model. We can simplify that in terms of the min PO2. We simplify that in terms of the min temp. Based on the min temp, or the mean temperature, I can then calculate the P crit that I think that organism would face if they were in that layer. So kind of it's high here and it goes down, 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 just like that. So that is an organism specific or a species specific estimate that's based on the environmental temperature and also the body size of the organism. So here's just an example of taking that one point in time and looking at just one particular depth. And what we're going to do is in the line that's super squiggly is that's the environmental PO2 over the course of the year, starting in January, very high in April and May, comes down, it gets low. This is in sort of mid-December, and then it comes back up. So these are bottom layer PO2 measurements. So that's the environmental signal that we're looking at. And then this little dotted line on the bottom is what would be the oxygen threshold for this routine moving around for a Dungeness crab if it was living on the bottom. And it looks super flat just because the scale is so big, but it is going up and down because the temperature is changing. It just doesn't change nearly as much as this environmental signal is going. And the key thing in all this is you probably paid attention right about here. That's a point where we flipped over, whereby the environmental oxygen is less than the threshold. So that's the thing we want to be paying attention to, is when and where are places where the environmental oxygen has dipped below the threshold. Now, one last flourish here is we could show you those plots for a gajillion places, but then we'd have to show you two lines for everything, and it gets kind of confusing. So instead of just showing both the min PO2 and the P crit, instead what we're going to be showing you going forward is the ratio of those two. So for each layer, what we do is we take what was the actual PO2, and we divide that by the p crit, and then we're going to get this number that looks like this. The actual numbers don't really matter. And that's just the ratio. What was the environmental oxygen relative to the threshold? So a value of 1 means that we were exactly at the threshold. Numbers greater than 1, meaning the environmental oxygen was greater than the threshold, and values less than 1 means we drop below the threshold. So going forward, we'll be showing that ratio in all the plots. So here's that same graph I showed you before, but instead showing you as that ratio. It's the ratio of what was the environmental oxygen relative to peak crit. It basically shows the same thing, blah, 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 blah. Boom. Here now we drop below the threshold, and then it came back up. Okay, one last thing. But here I've only been showing you single lines as if we knew the peak crit perfectly, but we don't know the peak crit perfectly. Laboratory studies, they still have some uncertainty in the numbers. And sometimes what we're doing is we're using information from a related species to say something about it, the species we care about. And that also introduces imprecision in our estimates of what the peak crit is. So another way we can look at the same graph is add in uncertainty bars, a confidence interval, and that ratio of PO2 to P crit. And all of that uncertainty, the error bar, is due to the uncertainty in what that P crit, that physiological threshold actually is. So that shows you on this particular graph, this is our best estimate in the line here. And then the gray bar is like the lower bound of what we think is plausible. And then you see the lower bound of that crosses the threshold obviously a lot more frequently than our best estimate. Okay,